Okay, so we just went through two sort of rich examples of kinematic problems in one dimension, a single object in motion and a sort of a catch-up problem with two objects in motion. And that's pretty representative of the kind of kinematical problems that you encounter. So now what I'd like to do is extend our kinematics in one dimension to kinematics in 3 dimensions. And the way we do this is we just go from just dealing with the x component of position, velocity, and acceleration to vectors, x, y, and z components. Okay, so x as a function of t, that will go to a full position vector r as a function of t equal x of t I hat plus y of t j hat plus z of t k hat. And similarly, our velocity, which we were just referring to as v of t, is really vx of t, goes to a full velocity vector, three-dimensional velocity vector, whose x component is vx of t, and whose y component is vy of t in the j hat direction, and whose z component is vz of t in the k hat direction. And similarly, the acceleration, okay, which we were just calling a of t, but really meant the x component of the acceleration as a function of time, will become a full three-dimensional acceleration vector whose x component is a of t, that's in the I hat direction, whose y component is a y of t, that's in the j hat direction, and whose z component is a z of t, and that's in the k hat direction. Okay? And so the most important thing to understand about this is we had a relationship between position, velocity, and acceleration in one dimension. Those relationships stay the same for the y components of position, velocity, and acceleration, and the z components of position, velocity, and acceleration. So basically we have three independent copies of what we did before. Okay, so we have an object in general moving on some general trajectory within three-dimensional space, and the relationships between r, v, and a are exactly the same as the relationships we talked about between just the x components. Okay? And so what we're going to end up with is two basic kinematical laws. Okay, so the first law, again, just follows from the basic definition of velocity. So the velocity, the full three-dimensional vector velocity of any object is equal to the time rate of change of the position vector. Okay? And so then what we can do is we can play the same sort of game. We can multiply both sides by dt. And so what we get is dr, an infinitesimal change in the position of the object, is equal to the velocity of the object at that instant of time times the infinitesimal change in time. So meters per second times seconds is meters of displacement under that velocity, in that direction. Okay, the displacement is in the direction of the velocity. dr is proportional to the velocity. Okay? And then what we do is we integrate both sides. So we integrate this side and we integrate this side. We integrate this from the initial position, r initial, to the final position, r final. And we integrate this from the initial time, t initial, to the final time, t final. Okay? And so let me just sketch a picture of this. So let's sketch it over here. So here we have, let's just sort of sketch it over here, maybe. Okay, and so we have some kind of an origin here, and we suppose that the initial position of the object is here in three-dimensional space. So relative to the origin, we need to displace ourselves by this three-dimensional vector r initial. That will take us to the initial point of the object, initial position of the object, and then let's suppose that that object moves on some crazy trajectory like this and ends up over here. Okay, and so this is the final position, and this is the vector. This is the final position. This is the vector, which tells us where that final position is relative to the origin. So that's our final. Okay, and so when we look at this picture here, remember that the velocity at any instant of time also is always tangential to the trajectory. So in this case, the velocity is changing in some crazy way, okay, from some initial velocity like this to some final velocity like that. And so then dr, the integral of dr, is the same as in one dimension. What we do is we add up all of the infinitesimal changes in position, and that gives us the finite change in position delta r. And in the same way as, taking the x component of the velocity, integrating over time, gives us the area under the velocity versus time curve, and that gives us the displacement in the x direction. Similarly for y and z. And so that area under the, x and y components of, velocity versus time can be represented as an average velocity, the average, times the time interval, delta t. So the question is, this object is moving with some crazy velocity, okay, and getting from here to here, it's moving with some complicated time-changing velocity. And what we're asking is, with what average constant velocity could it be moving for the same time interval to undergo the same displacement? Okay, so this delta r here is equal to r final, so delta r is equal to the change in the position, r final minus r initial. So we take r final and we add the negative of r initial, or r final minus r initial is the displacement vector to get from the initial point to the final point. And so this is delta r here. That's delta r. And that delta r is v average times delta t. Or in other words, we can write this as v average is equal to delta r divided by delta t. And so we just take this vector delta r, we divide by the time it took to travel this whole distance, and that will give us a vector in the same direction as delta r, but just scaled differently. And so this would be v average. So the average velocity is in the direction of the net displacement. And if you moved at that average velocity, constant average velocity, you would get from here to here in the same amount of time, delta t. That's the meaning of v average. Okay? So, so we have that. And similarly, if we look at the second basic kinematical formula, we have, it just follows from the definition of the acceleration. So the acceleration is defined as the time rate of change of the velocity. So a is equal to dv dt. We play the same game we did before. We say, yes, multiply both sides by dt. That leaves a dv. There's during a small interval of time dt, the infinitesimal change in the velocity is equal to the acceleration that the object is undergoing at that instant of time, times the amount of time dt. Meters per second squared times seconds is meters per second. That's the change, the infinitesimal change in the velocity. And then we do the same thing. We integrate. We sum all of the little changes in velocity from v initial to v final. And similarly, we sum over a dt from t initial to t final. Okay? And so what we get is, on the left-hand side, if we add up all the little changes in velocity from this velocity to this velocity to this velocity, if we add up all those changes in velocity, we get the net change in velocity, delta v, where delta v is equal to v final minus v initial. Okay, and that is equal to, in the one-dimensional case, it's the area under the acceleration versus time curve. And then we say, well, under what constant average acceleration could that object be moving to undergo the same change in the velocity? So we said delta v equal to a average times the finite time interval delta t. So this here is a fundamental kinematical formula, and this is a fundamental kinematical formula. This is like delta x is equal to v average in the x direction delta t, and similarly for y and z components. This is delta vx is the average velocity in the x direction times delta t, and similarly for the y and z directions. So it's the same formula written in vector form. Okay? Great. Now let me give you an example to help illustrate all of this stuff. Okay, so let's consider this. Let's go back to our really simple example of constant acceleration of the baseball under a free-fall parabolic trajectory. Okay, so if the acceleration is constant, and it is, because the acceleration is just of magnitude g, pointing straight down, everywhere along the trajectory, it's the same acceleration. And so if that acceleration is constant, then we have two facts. We have that the average velocity, v average, is going to equal the initial velocity plus the final velocity divided by 2. So it's going to be 1/2 v initial plus v final, and also the average acceleration. Average acceleration is just going to equal that constant acceleration. Okay, so we can use these two to specialize these two formulas to constant acceleration. So to see that, here's our baseball thrown on its parabolic trajectory. So let's suppose it starts on the ground and ends on the ground sometime later. Just have some symmetry in the problem to make it a little bit easier. And then, so this is the, this is, say, doesn't matter what axis, but this is the initial position, this is the final position. And so we can take our coordinate origin, let's do a picture something like that. Well, it's just going to make it a little bit messier. Anyway, so we start like this, and we say this is the initial velocity vector, v initial, and this is the final velocity vector, v final. And because of the symmetry, we know that v initial and v final have exactly the same length, and they are pointed at whatever 30 degrees up here, and then 30 degrees down. Okay, so these are symmetrical, v initial and v final. And under the whole, during the entire trajectory, this object is undergoing a constant acceleration of magnitude g pointing straight down. So the velocity is constantly changing. Okay, and so we can look at, say, let's look at this second equation first. Okay, so what this second equation is saying is that delta v, the change in the velocity, that's v final minus v initial, that's supposed to equal the average acceleration, which is just a times delta t. So let's see graphically how this makes sense. So we take v final, we write that down graphically, and that looks like that. And then we want to subtract v initial. So v initial is this vector. You want to add the negative of that vector, so that's a vector pointing down like that. So the negative of v initial is same as positive of this vector. And so you look and you see, the horizontal component of this vector cancels the horizontal component of that vector, and we were just basically adding the two vertical components of those vectors. And so we get a vertical component and a vertical component. So a vertical component of twice the length. Okay? And that's supposed to equal the average acceleration, which is constant in this case, times delta t, a delta t. And that makes sense because the acceleration is pointing down, and that acceleration is acting for a time delta t, and so the change in the velocity better just be down. And you can see that because if you start with this initial velocity, okay, this is v initial, and then this is v final, just sort of put them at the same base point. Here's v final. That velocity is smoothly changing from this to 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 this. And there's no acceleration in the horizontal direction, so the vertical component, so the horizontal component never changes. So after 1 second, say, that velocity vector changes to this. It tilts a little bit and gets a bit shorter. And then after 2 seconds, say, it tilts a bit more and it gets shorter. Now we're up here, and then it gets longer, and then it gets longest here. Okay, so this is the initial velocity vector. This is the velocity after 1 second, after 2 seconds, at the top of the trajectory, after 3 seconds, after 4 seconds. You'll notice that the velocity vector is rotating. That's one thing that's happening, and that's because there's a component of force or acceleration in a direction perpendicular to the motion. That's causing the rotation of the velocity vector. And then you also can see that the velocity vector starts out long and then gets a little shorter, It's shortest right here, and then it gets longer and longer. So it's slowing down on this portion, and that's because there's a component of acceleration pulling back. Okay? And then it gets longer, the speed increases, and that's because when you're over here, there's a component of the force in that direction, the direction of the motion, and that's increasing the speed. So the vector starts out shortest up here and then gets longer and longer. The speed increases, but the x component, the horizontal component, never changes because there's no acceleration in the horizontal direction. Only the vertical component of the acceleration is smoothly changing from v initial to v final. Okay, so that's just having a little bit of a look at that equation, how that equation makes sense. We can also look at this equation, delta r is v average delta t. So delta r is just a vector that points from the initial position to the final position. This is the initial position, this is the final position, so this vector right here that connects that point to that point, that is delta r. How do I want to write this? Yeah, delta r. And delta r is equal to v average delta t. Okay, and what is that v average? Well, that v average, if we're dealing with constant acceleration, v average is always the initial plus the final divided by 2. It's the midway point, in this case between two vectors. Okay, it's the average of those two vectors. And so v average is equal to, let's work it out graphically. Take v initial, and then we want to add tip to tail v final. Well, this is v final, put that here, that's v final. And then the sum of v initial and v initial plus v final is this vector. And then we divide by 2. So take that vector, divide by 2. This vector right here, this is v average. Okay? And you can see that the average velocity has only a horizontal component, because the initial velocity had a positive vertical component, positive vertical component, and then negative vertical. And the positive verticals and the negative verticals canceled out, and all that was left was the positive horizontal component. The average velocity is just the x component of the initial velocity, because with projectile motion, there's no acceleration in the horizontal direction. Vx never changes. And so that's just the average velocity is just the x component of the initial velocity. So you see how those things work out? And yeah, so that's that. And then a final thing to think about here, in going from our one-dimensional kinematical formulas to our two-dimensional kinematical formulas, you'll remember that when you substitute, when you assume constant acceleration, then you have, A average is A and V average is this, and then you can, plug one equation into the other and you can generate more equations. So I'm going to do this for the two examples we did in one-dimensional. I'll do this for three-dimensional motion. So let's start with this kinematical formula. Okay, so delta x is equal to v initial, vx initial delta t plus 1/2 constant acceleration in the x direction times delta t squared. And now we wonder, how could we generalize this formula to a three-dimensional formula, a full vector formula? Well, so if you just think a little bit about it, delta x, this is the displacement in the x direction. Okay, but if we're moving in general three-dimensional space, there will be a displacement in the x direction, the y direction, and the z direction. And so really delta x gets replaced with delta r, where delta r is a full three-dimensional vector. It's here r final minus r initial. It's that vector in three-dimensional space. So delta r is going to equal, we need a vector on the right-hand side. This is actually the x component of the initial velocity. If we include consideration now of the y and the z components, this x component of initial velocity will become the full three-dimensional initial velocity vector, okay, having x, y, and z components times delta t. And then the last one, similarly, this is the acceleration, the constant acceleration in the x direction. Okay, if we're dealing with constant acceleration in general in x, y, and z, you will have a similar a y and a z term. And so when you add those all up, including I hat, j hat, and k hat components, you're going to get plus 1/2 the full vector acceleration times delta t squared. And so this is the vector version of this equation here for one-dimensional motion along the x-axis. This includes motion in the x, y, and z directions. And you can easily derive this in exactly the same way that we did before. Okay, so we have these two equations. Delta r is equal to v average t, delta t, and delta v is a average times delta t. So we can play the same sort of game. So we'll say under constant acceleration, delta r is equal to the average velocity, which is 1/2 the initial velocity plus the final velocity times delta t. And then we look at this equation here and we say delta v. Now delta v by definition is the change in the velocity, so that's v final minus v initial. Okay. And that's equal to a average, which is just a constant acceleration vector a, times delta t. Okay, and now we do the same thing that we did before. Okay, we look at these two equations and we substitute for v final. The v final from this equation gets substituted into there. And so we have delta r is equal to, let's see, 1/2 v initial plus v final. What's v final? Well, the second basic kinematical formula tells you that v final is equal to, take the negative v initial to the right-hand side, is equal to v initial plus a delta t, and then multiplied by delta t. And so you can see that you're going to have a vi plus a vi, that's 2vi, divided by 2 is just vi delta t, there's the vi delta t, plus 1/2 a delta t squared. Okay, so that's where that formula comes from. The other one is a little bit more interesting. The other formula that we had was, let's see if I can fit this down here. The other formula that we had was, what was it? V final squared minus v initial squared is equal to 2a delta x. Okay? And so if we wanted to generalize this to motion in 3 dimensions, this is going to be a little bit a little bit trickier. So on the left-hand side, we have a scalar quantity. This is vx final squared minus v initial final squared. And so this is like the sort of like the dot product of 2 vectors. And so just this is the final speed squared in 1 dimension minus the final speed squared in 1 dimension. Final squared minus initial squared speed. Okay? And so on the left-hand side, we might guess that this is replaced with v final, the full vector final velocity, magnitude, so the final speed squared, minus, instead of just the x component, you know, the speed squared in just 1 dimension, it'll be the full speed squared in initial. So final speed squared minus initial speed squared is equal to, this is a scalar, so on the right-hand side we need a scalar. Remember that this is ax. This is ax, the x component of the acceleration times the x component of the displacement. Well, the dot product between acceleration and displacement, the x part of it will be ax delta x. So on the right-hand side here, we need a scalar. So we can easily guess this is going to be the acceleration, the constant acceleration vector, a vector dot product with the vector displacement delta r. Okay, and yeah, so that's the second equation. This is a 3-dimensional version of this 1-dimensional equation. And you can see how to derive this. You play exactly the same game that we played in the 1-dimensional case. We say if this equals this, and this equals this, then this vector dot product with this equals this vector dot product with that. Okay, so on the left-hand side, we're going to have this vector dot product with that. So that's going to be an a delta t vector dot product with delta r. And then on the right-hand side, we're going to have is equal to this vector dot product with that. So that's going to be 1/2, say, v final plus v initial, v final plus v initial, vector dot product with v final minus v initial, v final minus v initial, and then times delta t. Okay? And so the delta t cancels from both sides, and so you can see that we're going to have this result. Taking the factor of 1/2, moving it to a 2 over here. Okay, so then we have v final dot v final, that's the magnitude of v final squared, minus v final dot v initial, plus v initial dot v final, those two terms cancel, and then minus v initial dot v initial, minus the initial speed squared, the magnitude of the initial velocity squared. So this reproduces the left-hand side, and then we have 2 times the vector acceleration times the vector displacement delta r. Okay? And just as a quick sort of example of that, let me just go back to this case over here. So this is kind of interesting. So we notice here, we know just from symmetry that the magnitude of v final, that's the final speed here, is equal to the magnitude of v initial. So in this equation, v final squared minus v initial squared is the square of the speeds. The difference should be 0, just from symmetry. So the left-hand side should be 0. Is it? Well, you can see easily that delta r, what's the vector delta r? Well, it's the displacement from here to here. That is a horizontal vector. What is the acceleration? It is a vertical vector. Okay, and horizontal and vertical vectors, their dot product is 0. So this is also 0. Okay, so anyways, this is these are the two basic kinematical formulas for 2- or 3-dimensional motion, or 1-dimensional for that matter. These, and this is the second one. Okay, these two follow from the basic definitions of velocity and acceleration. You get these two relationships, which are always true. In the special case of constant acceleration, V average is this, and A average is this. So whenever you're solving a problem, just write down these two equations, specialize them if it's a case of constant acceleration, specialize them to the constant acceleration case, and then start plugging in things that you know, and then you generate a bunch of equations, and then you solve those equations for the unknowns. And that's basically it. So I think that concludes our introduction to kinematics, which basically reviewed kind of stuff you did in high school with kinematics, but it raised it up a notch. The hope is for you guys to get a little bit further than high school. Okay, so I try to do that by introducing vectors, more vector-based discussion of kinematics, and also, moving away from numerical solutions to algebraic solutions and so on. So I really encourage you to, go through these lectures and really try to master this material so that you can notch yourself up from sort of high school. Here's second year, right? We had this diagram before. Phys 121 lies somewhere between high school and second year. We've really got to notch you up here. This jump is huge. Okay, so if you can manage to get through this jump, then it's about an equal-sized jump to get to second year. Okay, so yeah, so that's it for kinematics.